Hi, I'd like to talk to you about normalization by evaluation for Fitch-Style model Lambda calculi, and this is joint work with Fabian and Carlos. So by modal, in this talk, I'm referring to the modal logic intuitionistic K, and this logic extends intuitionistic propositional logic with a unary connective box, the necessitation rule, and the so-called axiom K. We're interested in studying a lambda calculus which models this logic, specifically the Fitch-Style lambda calculus lambda ik, which is formulated by extending the simply type lambda calculus with a delimiting context operator, denoted here by a lock. The lock is used to formulate the introduction and elimination rules for the box type former. The introduction rule removes the lock from the context, and the elimination rule adds the lock to the resulting context. There's also a slight modification to the variable rule in the simply type lambda calculus. To get an intuition for the system, note that by assuming something of type A alone in the context, you cannot prove something of type box A. Similarly, given box A, you cannot produce something of type A. On the other hand, given something of type box A times B in the context, you can produce something of type box A. And given both box A and box B in the context, we can produce something of type box A times B. We want to study normalization by evaluation, or NBE, for lambda ik and for Fitch-Style model calculi in general. And this is because modal lambda calculi have many different applications in programming languages. So we may interpret the box type box A in the context of staging as code of type A, or sensitive values of type A in the context of security, or we may interpret them as pure values of type A in an impure language, such as ML. NBE can be used to prove many theorems of interest. So for example, we can prove non-interference in the context of security using normalization in a syntactic fashion. But NBE can also be used to prove more general results such as completeness for lambda ik, as we will see later. So the standard theory of normalization by evaluation proceeds as follows. We start out by interpreting the terms in our calculus in a suitable semantic domain, but it's not just any semantic domain. It's a semantic domain which supports the operations of reification and reflection. Reification converts values in the semantics to normal forms, and reflection inserts neutral elements into the semantic domain. The normalization function is implemented by evaluating or interpreting the term with the identity environment, and then reifying the resulting value into normal form. So for the simply type lambda calculus, the evaluator is given by the generic interpretation of the simply type lambda calculus in a Cartesian closed category, and the NBE model is given by considering presheaves over the category of context and order-preserving embeddings. For lambda ik, we proceed in a similar fashion. We use the generic interpreter of lambda ik in a Cartesian closed category with a pair of adjoint functors, as identified by Clouston. And for the NBE model, we use presheaves over the category wlock, which is defined similar to W, except now we also require that the morphisms or order-preserving embeddings must also preserve locks in the typing context. What remains for us to do is to identify a suitable adjunction on the category of presheaves to complete the construction of our NBE model. So we can implement or define these adjoint functors as data types in a programming language such as Agda using data types box and lock, where the type box removes the lock from the context of a semantic value, and lock, on the other hand, adds the lock to the context of a semantic value. Observe the resemblance between the introduction and elimination rules for the box type former. Using this setup, we can interpret the term formers, box and unbox, and we can also implement reflection and reification for the box type. So this completes the construction of our NBE model, but we can also reconstruct this NBE model in a more generic fashion using the possible world semantics of lambda ik. So the lambda ik's possible world semantics is parameterized by a frame constituting of a set of worlds and two binary relations on the set of worlds, subject to certain conditions. We can reconstruct the NBE model by picking contexts for the set of worlds and order-preserving embeddings that preserve locks for the ordering relation. And we define the relation R to be lock-free extensions of a context after the addition of a single lock. So this instantiation gives us the NBE model that we had constructed up to this point. The reconstruction of this model corresponds to the completeness, a constructive completeness proof of lambda ik's possible world semantics. So we've talked mostly about lambda ik and the axiom k up to this point, but we're also interested in axioms beyond k because they're more useful for other applications. So the corresponding AGDA mechanization and the work in progress code can be found in the repository. Thank you.